According to this problem, there is a solid sphere which has a radius r, and the bulk modulus of its material is given as K. And this solid sphere is kept in a container containing some liquid. Okay? A massless piston of area A floats on the surface of the liquid, covering the entire cross section of the cylindrical container. Now what happens? Some mass m is kept on top of the piston. You have to find out what is going to be the fractional decrement in the radius of the sphere. And fractional decrement is dr by r. So how it happens, you can look at this simple animation. Mass is kept and the piston is going down, right? So the concepts in this case are pressure and bulk modulus. And the question is easy. So let's start solving. Well, if you remember the definition of bulk modulus, then K is defined as dP divided by minus dV by V, right? Or you can say K is minus V dP by dV. Now what is the change in pressure? Well, the change in pressure is due to the mass, right? So the force due to the mass is m into g, and the area of the piston is A. So we have the change in pressure dP to be equal to mg divided by A. Agreed? And now what is dV by V in terms of dr by r? Because remember, we have to find what is the magnitude of dr by r. And by intuition, we can tell that the volume is going to decrease. That is, the radius is going to reduce. So we know that the volume of a sphere is 4 by 3 pi r cubed, right? And can you see from here, dV by V is going to be equal to 4 by 3 pi is a constant, and this will be 3 dr by r. And we are almost done. So let's put the values here. K is going to be equal to mg divided by A, right? By, and this is dV by V, that is minus 3 dr by r. Correct? And from here you will get dr by r to be equal to minus mg divided by 3 Ka. And the magnitude of this, which is asked in the problem, is going to be mg divided by 3 Ka. And you can take option C as the right option. We have 2 moles of an ideal monoatomic gas whose initial temperature is 27 degrees Celsius and the initial volume is V. Now the gas expands adiabatically to a volume twice its initial volume, that is 2V. You have to find out the final temperature of this gas and the change in its internal energy. So what do you think are the concepts which are involved? Well, we have the adiabatic process and internal energy. And this problem is easy, as most of the problems from thermodynamics are. So we know that in an adiabatic process, no heat can come into the system and no heat can leave the system, right? And we know that in such a case, PV raised to the power gamma is a constant. And if we combine that with PV is equal to nRT and get the expression in T and V, then you already know that TV raised to the power gamma minus 1 is going to be a constant, right? So T1 V1 gamma minus 1 is going to be equal to T2 V2 gamma minus 1, right? Where we have T1 as 27 degrees Celsius, which in Kelvin is 300 Kelvin, right? And according to the question, V2 is 2V1. So V1 by V2 raised to the power gamma minus 1 is the final temperature T2. And V1 by V2 is 1 by 2. Now let's calculate what is gamma. Well, we know that gamma is Cp by Cv, right? And for a monoatomic gas, the degrees of freedom are 3. Right? It can move along x, along y, and along z. So Cv is going to be equal to 3 by 2 into R. And for an ideal gas, we know Cp minus Cv is equal to R. So Cp comes out to be 5 by 2R, which makes gamma 5 by 3. Right? So the final temperature of the gas is going to be equal to 300 by 2 raised to the power 5 by 3 minus 1, that is 2 by 3. Comes out to be approximately 189 Kelvin. So the final temperature of this ideal gas is going to be 189 Kelvin. And can you see that the temperature has decreased, right? And in the expansion process, the gas would have done some work. And you can see that the work will be done on the expense of internal energy, right? So logically, the change in internal energy should be negative. And this makes sense because internal energy only depends upon the temperature. And can you see that the final temperature of the gas has reduced? And we can use the formula to find out what is the change in internal energy of the gas. We know that change in internal energy is going to be equal to NCV delta T, right? Number of moles are 2. What is Cv? Well, we found out Cv to be equal to 3 by 2R. And the change in temperature is final minus initial. And from here we will get the value of change in internal energy to be equal to minus 2.7 kilojoule. So in this case, we can see that option 3 is going to be the right option. So hydrogen molecules are bombarded on a fixed wall and the collision is perfectly elastic. You have to find out what is the pressure on the wall. Mass of each hydrogen molecule is given to you. It has been mentioned that 10 raised to the power 23 hydrogen molecules strike the wall in each second. The speed of the hydrogen molecules is given out to be 1000 meters per second. And the angle made by the normal is 45 degrees. So in this case, the concepts involved are elastic collision and pressure. And conceptually, this problem is easy, just that the calculation is going to be little tedious. So to find out the pressure, we know that pressure is force per unit area. We know the area. All we have to do is find out the force, which we can find by finding the change in linear momentum of the molecules in each second, right? So let's assume that the mass of each molecule is some m. Okay, I'm assuming this to be some m. We'll put the values later. So the situation is something like this. Comes like that and rebounds like this. This angle is 45 degrees. Let's say this is theta. Okay. So the linear momentum initially is along this direction and the magnitude is m into v. And finally, after the collision, the linear momentum magnitude remains m into v, just that the direction is like that. Now can you see that the linear momentum parallel to the wall doesn't change? So there is no force applied along the direction parallel to the wall. In the direction perpendicular, the magnitude of the linear momentum remains the same, just that the direction is reversed, right? And let's find out what is the change in linear momentum of one molecule first. So this is going to be 2mv cos theta, right? And there are 10 raised to the power 23 hydrogen molecules colliding with the wall in each second. So the change in linear momentum in each second of the molecules is going to be 2mv cos theta into 10 raised to the power 23, right? So you have found out what is the force. And now let's use the formula. So pressure is going to be equal to 2. Let's put the values. What is m? Well, m is 3.32 into 10 raised to the power minus 27. V is 1000, that is 10 raised to the power 3. Cos 45 degree is going to be 1 by root 2 into 10 raised to the power 23 divided by, and the area of the wall is 2 centimeters square, that is 2 into 10 raised to the power minus 4 meter square. And once you simplify this, you will get the pressure to be equal to 2.35 into 10 raised to the power 3 Newton per meter square. So in this case, you can see that option A is the right value of the pressure on the wall. So in this case, a silver atom is performing simple harmonic motion with a frequency of 10 raised to the power 12 oscillations in each second. You simply have to find out the force constant of the bonds connecting one atom with the other. And then you have to choose the right option. So in this question, the concepts involved are simple harmonic motion, frequency and force constant. And the level is easy. Now recall the case when the block of mass m is connected to an ideal spring of spring constant k. In that case, the frequency of oscillation turns out to be 1 upon 2 pi under root k by m, right? Well, this case is no different. The place of an ideal spring is taken by the bonds. That's it. So we can use the same formula to find out the force constant k. If you square both the sides, then this becomes f square is equal to 1 upon 4 pi square k by m, where m is the mass of one silver atom. And from here, the value of the force constant turns out to be 4 pi square f square into m. Now you can take the value of pi square approximately 10. Okay? So everything is known except m. And this can be found by using the molar mass of silver. So 6.02 into 10 raised to the power 23 silver atoms have the mass of 0.108 kg, right? This means that one silver atom will have the mass of 0.108 divided by 6.02 into 10 raised to the power 23 kg. And when you put it here and solve, you will get the value of K to be equal to 7.1 Newton per meter. And this is your final answer. So you can tick option B as the right option. Let's solve this one. In this case, the question talks about a granite rod which has a length of 60 centimeter and it is clamped at its middle point and is set into longitudinal vibrations. The density and Young's modulus are given to you. You have to find out the fundamental frequency of the longitudinal vibrations. Pretty easy, right? So what are the concepts involved? We have waves and fundamental frequency in this case. And the level is easy. So let's assume this is that granite rod, which is clamped at its middle point like that. Now for the fundamental frequency, the vibrations will look like that, right? Where you can see that the length of the rod is equal to lambda by 2, correct? So lambda is 2L. And we know that frequency is going to be equal to velocity of the wave by lambda, correct? Now how do you find out the velocity? Well, we know that the velocity depends upon two things. One, the density of the material, and two, the Young's modulus. And if you remember, velocity is under root y by rho, right? So we have the frequency to be equal to 1 upon 2L under root y by rho. And L here is 60 centimeters, so this is going to be 1 upon 2 into 0.6, that is 1.2 under root. The Young's modulus is 9.27 into 10 raised to the power 10 Newton per meter square divided by the density 2.7 into 10 raised to the power 3. After simplifying, you will get the value of the frequency to be approximately 5 kilohertz. So in this case, the fundamental frequency of longitudinal vibrations is going to be 5 kilohertz. So three concentric metal shells A, B and C have the surface charge densities as plus sigma, minus sigma and plus sigma. You have to find out the potential of the shell B. Simple, right? So the concept tagged is electrostatic potential, and obviously the level of this question is pretty easy. Do you agree? Yeah? You would have solved a lot of problems on the similar concept. So let's assume that on the shell A, QA amount of charge resides. Okay? On shell B, the amount of charge is, let's say, QB, which we know is going to be negative, but we'll see about that. And on the shell C, let's say the charge residing is QC, where you know that QA is going to be the surface charge density into the surface area, that is 4 pi A square. QB is going to be minus sigma into 4 pi B square, and QC will be sigma into 4 pi C square, right? So these are the charges on each shell. And now to find out the potential of the shell B, we know that A, B and C, all three are going to contribute to that potential, right? So the potential is going to be potential due to the shell A plus potential due to B itself plus potential due to C. And you know that potential is a scalar quantity, right? And now let's put it one by one. Let's assume that the value of K is 1 upon 4 pi epsilon naught. So the potential is going to be, now can you see that for the shell A, shell B lies outside of it. So VA, or you can say that potential contribution due to shell A is going to be KQA divided by B, right? Due to itself, it is going to be minus, or first let's put it in terms of QB only. So plus KQB divided by B plus, and for the shell C, shell B is lying inside of it, right? So the contribution due to shell C is going to be KQC divided by C. And now when you put the values of the charges and the electrostatic constant, then you will get the potential of the shell B to be equal to sigma upon epsilon naught A square minus B square by B plus C, as simple as that. So in this case, option B will be the right option.